I think he's mainly a geometer, but he has a good taste for several things, including recreational mathematics and classical analysis, if I recall correctly, right?
Yes.
Okay.
Okay. Thank you very much, Jorge Nuno. So I'm kind of, teaching geometry, doing research, and this is kind of a side, interest, which in fact I think started when I discovered this game, Tantrix, when I was spending some vacations in Algarve. I was in a cafe and didn't have anything to do with my kids while my wife was taking a nap, and I took my little kid was 2 years old, and I went to this cafe near a swimming pool, and the woman there had this thing there. So I was curious, and she said immediately, please, you need to have an explanation. And this is a very important thing because it's very hard to find in Portugal. It was a gift by a Canadian guy or something. And she explained me, and I was fascinated with the game, also my kids, I guess. Okay, so this is, I'm talking about this puzzle, but in fact, there was a game, which is that one, that was kind of invented before. And the puzzle was like something that is actually more mathematical, because the game has the luck involved. So what is the origin? So this, I'm sorry, it's in Portuguese, but this is a presentation with colleague Pedro Freitas that we did in the fifth, history of games, that was a meeting. Okay, so the origin is New Zealand. This is the antipodes of Portugal, basically. This is a map with the globe and the antipodes. The creator, Mike Manaway, in 2014. So he invented a game that was also had luck on it. I think he was interested in backgammon, and he was in fact I think a champion of New Zealand of backgammon. He wanted to create a game with some luck, mainly because of the following reason. If it is only for strategy and mathematics, the kids is going to win to the adults. So this game is to be like a family game where the grown-ups can also win, if they have luck, because the kids typically learn it faster and have more memory and things like that. Okay, so what are the pieces? The pieces is as you have. Every piece is an hexagon, right? And it has 3 lines connecting, the sides. There are 4 types of crossings if we disregard the colors. So we have the no crossings. We have also no crossings with a straight line. We have 1 crossing. This we call corner. We call this a corner, and we call this bent. This is a straight and 2 crossings. There's actually a fourth. Maybe I can use the chalk.
On the box.
Yes. There's also, in fact, of course, a fourth type of crossing, which would be this one, right? With the 3 colors, right? Every piece has 3 colors, but this ended up not to be good for the game, just for the game. In fact, it could be used for the puzzle as well. But for the game, Mike Manaway understood that this is not a good piece to have when you're playing the game. I'll explain a little bit why. So it was not used. Okay, so I guess with these 4 types of crossings or 4 types of tiles, we can now put colors, and we have, for example, 2 colors for this one, because it's either red, blue, orange, red, blue, yellow, or red, yellow, blue. And the rotation, takes care of the rest. So it's only 2 for this, 3 for this, because the center is a special color, and the other 2, whatever, because you can rotate. 2 for this one. 6, this one, because this can be red, and these are the 2 other ones, but you can have the 2 crossings the other way. 6 here and 3 here. So in total 14. Okay. So what are the rules of the game? So the game is what Marcus has. The idea is the following. Every player has a color, decides on a color, and tries to create the longest possible path of that color. That's easy, right? So in the end, we have 56 pieces in total, right? Or tiles, let's say. Because there are 14 times 4, because there are 4 colors. Yeah, in the puzzle only 3 colors, but in the game there are 4 colors. And so we try to make the longest line with one rule. If we have a loop, they will be counted twice. So the number of pieces that the line passes through is the number that number that is counted in the end. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for example. But if there is a loop, right, the 10 would count 20. So you need to be careful not to close your line very soon, and if you close it very late in the game, you basically win, typically. But you also want to kind of block the opponent line. Of course, it can be played by 4 people. But there is luck. Why there is luck? Because every piece is different. This is like a deck of cards, in a sense. It's like playing with a deck of cards, but the deck of cards would be like a one-dimensional game. A card game is like a one-dimensional game, because you put one card, there's another one, there's another one. I mean, it's like always in one. This is a two-dimensional game. That's how I like to think about it. I mean, so it's slightly more complicated. So what are the rules? This is always the rule in force. It's called the golden rule. It means that we can only, when we connect one tile to 2 others, we need to follow the colors, right? All the colors need to follow, so this is wrong. And even if I put a blue here and a red here, that would be wrong. Even if I have a blue color, I need to connect all the correct colors always. This is because, so if these pieces have been played, and I want to play this piece, even if I have this piece, I have to put it here. So it's a mandatory movement, because this is called the Tantrix. So all the pieces that have been played already called the Tantrix, right? And if I have a piece like that one, I need to put it, just because the geometry would become too complicated if I don't go on, right? I mean, it's just made to make the game more pleasant and not very wild or something like that. And then there are also some forbidden rules. For example, forbidden moves. Mm-hmm. This is forbidden because this is red, 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 and there is no piece that has 3 reds. As it's obvious, because every line, every color has only 2 edges, right? And this is also forbidden. If I have this, if somebody has this piece that fits here, it's forced to play here. But if I have a piece that comes here, this is forbidden now, because it's also too complicated to have a piece. If there is a 4th edge here, it would be very complicated to put a piece here, and basically that would mean that the yellow, for example, the yellow line is blocked forever, and the blue also, for example, this blue also, and that would be complicated. So you cannot play here or play here when you have this, what is called the forced space. This is a forced space because it's mandatory to fill in, and similarly here, because if I play Z here, then this becomes a forced space. If I play Y here, then this becomes a forced space, and then I put here, and then this would contradict that rule there. So when I have like a side here, I have to fill out this one first, always. This is a forced space, and you have to fill this out, and then this one, and then this one, whatever, right? Okay, so this is basically the games of the rules of the game. So there's a booklet with which explains everything. But also then the inventor of this game understood that this has a lot of interesting symmetries, patterns, so you can do a puzzle with it, which is now then can be studied mathematically, and this is what has got me interested, I guess. So I have an interest in things that has patterns, shapes, everything that has to do with geometry, I guess. And also I try to, like I guess Euler or other mathematicians, when they solve this Königsberg bridges problem, you want to extract the useful information and drop the rest. I mean, you want just to see what are the combinatorics involved, right? You want to remove all the things that are irrelevant. So, I mean, okay. So this is this is some events that we also promote sometimes. And kids, of course, like to play this. These are very interesting pieces that I didn't manage to bring today that are very big. And the peeling.
Yesterday at the museum.
Okay.
At the
Yeah.
museum.
Yeah, in the museum there's this. Okay, and so there's also this online page that's been up for 20 years or something. Okay, so what is the puzzle? So I'm now going to explain the puzzle. The puzzle is the following. You have pieces that are numbered. So maybe I can use this one if you don't mind. So we have pieces that are numbered. So 1, 2, 3. We start with 1, 2, 3. Okay. With these 3 pieces, the third piece is yellow on the back. So you form a yellow circle. So the puzzle is always to do loops. Always loops and circuits, closed circuits basically, right? So the fourth piece in the back, the number is red. So you are supposed to make a red circuit, red loop. And there's basically one solution, only one solution. So then the 5th piece is also red, you can do also and so on, right? And I think what is nice is that, I mean, there's a sequence where you typically have only one possibility of making a loop. For example, here you could imagine that, I mean, it's impossible to do, with these 5 pieces, it's impossible to do a yellow loop or a blue loop, in fact. You can see it easily. The thing which is interesting is that, of course, you may think that it becomes more complicated, but in fact, it doesn't become too much more complicated. That's the good thing, right? And because also the number of solutions increases. And so I started to think a bit about the possible number of solutions of these things. Of course, with this just 10 pieces, you do 10 puzzles basically. Because by the way, the 10th piece, it's possible to do a loop in each of the colors. In fact, I mean it's in fact like that. So I started to think about how many solutions there are. This is for example, so basically with 3 pieces there's one solution and so on. This is yellow, red, I think 6 is blue, 2 solutions. And I counted here 2 solutions because the 2 solutions would be one right-sided and left-sided. We're counting differently. So for example, the 6th solution, there's one like this, but we can also do the mirror symmetric of that. That would be slightly different. I mean, it's just a convention. Verificar 4 solutions. Well, in fact, we have, there is a booklet, by the way, for schools. There is a booklet that we translated from English that has been used in some schools to teach some parts of to connect with some parts of the curriculum of the school, because it teaches symmetry, for example. I mean, or at least it applies to these ideas of symmetry and so on, right? Patterns and symmetry. And for example, one of the activities with the children is to construct all the 4 solutions of the 8th puzzle with 8 pieces. So we have 8 solutions, which this has 1 axis of symmetry, this has no axis of symmetry, this has 2 axes of symmetry, as you can see, right? The solution. So we kind of forget the other lines for this. But still, we forget the other lines, but the golden rule is always enforced. So I cannot So for example, here, this yellow line has to continue always, and the red line has to continue. Cannot change color in the middle. So this is always important. Okay. So I kind of started to try to see what would happen if I have an infinite set of tiles, Tantrix tiles, and I want to know how many solutions there are for each number of tiles, basically, right? So I have an infinite set of tiles, repeating all whatever, right? So this is what it means, this question. What about if I want to solve the problem without restriction of the number of tiles? I have all these tiles that I want at my disposal, right? And I want to form all, to understand how many solutions of the puzzle there would be. Okay? So then this becomes a problem of combinatorics, because every shape like this can be constructed in the following way. We can, instead of having the curves, we can connect every edge to the center and do like this, and this will become a tiling of the plane with triangles. So this is the next slide. We can do this, right? With every loop, Tantrix loop, we can associate like a polygonal line, joining the centers of every tile, and this is actually the dual pattern of the hexagon tiling of the plane. You know that the dual of a hexagon tiling is going to be triangular tiling, right? Because we do like this, right? Whenever we have this, we do, and this will be a. So the dual tiling is the one that we have a center in the vertex, replacing the center of the face, and every edge of the dual tiling is going to be perpendicular to the because this is regular, all those regular polygons, right? So we can do this. We can form the union of triangles like this, right? And this is now a known mathematical object called polyiamonds. So the name in English is polyiamonds, because this comes from this idea of diamonds, and also before is like this ideas of tiling with the plane with dominoes. So this is dominoes, this is diamonds, and this is polyiamonds, because it's just multiple sets of triangles. So I think it's clear the association between Tantrix loops solutions with an infinite set of tiles, let's say, and shapes like this. So I mean, somebody gave names to these shapes. So this is I have to see it here. I think rhomboid, club, crown, sphinx, snake, yacht, whatever, bat, pistol, lobster, and so on. Hexagon, butterfly. So you see, curiously, I mean, of course, with the puzzle that's a product that is sold, I mean, commercially sold, right? We can do only these three. But with an infinite set of tiles, we could do all the other ones, except in fact for this one, because there's a rule saying, I mean, of course, this is it's convention. Of course, I could make up another puzzle where this would be a solution, and in fact, this is a nice shape, because it's just if I do this, the boundary here, that would be a circle, perfect circle, done with pieces all like this one. This would be a circle like this. But in the rules, they say you cannot have a hole in the puzzle. So this means so this is not this would be a puzzle a Tantrix loop like this, but there would be a hole. I mean, with no tiles here. there would not be a tile here, so this is not a solution. So the hexagon like this does not form a solution. The hexagon polyiamond does not, it's not a solution of a Tantrix puzzle. So the question is how many solutions there are for Tantrix puzzles, and me and and Pedro, we started counting some of them, but we didn't have a computer to do it all the way. But this is just possible. So I think we need to remove this one, and that's it. We need to count these polyiamonds, but not everyone. So so the condition is the following: we need n triangles, and the perimeter n plus 2. It's always the idea. So it's an if and only if condition. If there is an inner vertex like this, the perimeter drops. But and it's not a possible Tantrix loop solution. But if there is no inner vertex, then it's a possible Tantrix solution, and it corresponds to, for example, 1, 2, 3, 4, 5, 6, right? This lobster shape, and you see easily that it has 1, 2, 3, 4, 5, 6, right? And it has perimeter 8. So 6 triangles, 8 edges, boundary edges. And so that's the condition. And in fact, so we were looking at the online encyclopedia of integer sequences, how many there are, and apparently this sequence is not yet there. So this is I don't know if you know this online encyclopedia of integer sequences.
I don't think it's common knowledge.
It's not. Okay. Okay, so there's a web page with nice, integer sequences that has been, sponsored by some computer department computer science department, and they put a lot of sequences that are of interest in combinatorics basically, and so we look at it. And I guess, so there is a sequence there that counts triangles with perimeter n plus 2, but does not care about the inner vertices. And there is another one, but also, the triangles could have holes as well, and that would be a problem. So this was just idea of a project that would be interesting to do. To count all these solutions. So this was just computed by hand, and so I guess I can just say a few words about the web page, because so this is a web page of the Tantrix. It has a way to play online. I think the problem is that my computer is not able to do the. It doesn't have Java, and this works only with Java or something. So this has, for example, I have here the number of players all time. They have a lot of rankings, and it's interesting. Of course, nil is first, and then Hungary next per capita, right? Players per million. Regular players, right? I mean, this is an online how do you say? It's a social game, that is running for at least 20 years, and you have a lot of countries, and not Portugal, basically, on the top 20, and we have Spain, but a lot of European countries as well, I would say. So in Hungary, I think it's an interesting situation because it's popular, right? Yeah, it's popular. It's a very interesting situation. I think it has to do with the fact that people are introduced to games, in school. With I think probably I don't know. So what else I can just say? I think yeah, this has also the online playing the game with a 56 tiles is interesting to do it online first because it actually prevents you to make a forbidden move and so on. Yeah, an illegal move. So it's fine. So I guess, yeah.
Thank you very much, Carlos.
Thank you very much.
Thank you very much.